Problem number 1. Let's say we have an infinite collection of sets AI such that A1 is a subset of A2, which is a subset of A3, etc. And AK exists for all natural K. So here's what we're going to do. We're going to show that the union of all of these sets, so the measure of the union of all of these sets is going to be equal to, wait, what was the actual result?
Excuse me, can you give a nice introduction? I completely lost it.
What?
Nice introduction of the problem.
Okay, sure. Let's say we have an infinite collection of...
No, look at the camera and give a nice
I can't. You want me to...
Yeah. Just look at the camera and give a Lebesgue measure introduction.
It's just... Lebesgue measure is a tool and analysis that we use that's dependent on the infimum operation that essentially generalizes the notion of length as we know it to sets that are not necessarily intervals or the union of intervals. Okay, so let's do a problem with the Lebesgue measure. Let's say we have an infinite collection of sets, AK, such that AK exists for any natural K, and such that A1 is a subset of A2, that's a subset of A3, etc. Or in general, AI is a subset of AI plus 1. Okay, so now, here's what we're going to prove. We're going to prove that the measure of the infinite union of all these sets AN is equal to the limit as n approaches infinity of the measure of AN. Okay, so how do we do that? Well, we can't use subadditivity because all the ANs are clearly not disjoint. So what can we use instead? Well, let's assume, well, the limit has to exist, right? Because let's think about it. The only way this could diverge is by continually expanding out to infinity. Because A1 is a subset of A2, is a subset of A3, and so on and so forth. You can't oscillate like the sine function with A1 being this big, A2 being this big, A3 being this big, A4 being this big. You can't have that. It's got to continually increase. So either it approaches a limit, or it keeps diverging out to infinity. In which case, the limit is just, well, you can't have it closed. So, the limit always exists, no matter what. Either it diverges and gives us that, because infinity and negative infinity are part of set theory notation, or, it converges to a limit because of this monotonicity. So, let's take the limit as n approaches infinity of an to be equal to b. Now, the continuity of the measure function tells us that this is actually this. So, this is just the measure of b. So now, what is b actually? How is it related to this? Well, if you already know your set theory, you might say, well, these are the same. But how do we prove that? Well, let's think about it really hard. So, this set AN has to be a subset of B, right? Why? Well, because this is going to contain every single set AN. So it's going to contain A1, then A2, then A3, then A4, etc., etc. And remember, if we stop at AI, for example, AI plus 1 contains all of these. We can already comfortably say that the union from n equals 1 to k of this is covered by ak plus 1. So now we just shove in a limit as k approaches infinity on both sides, and suddenly this is just, okay, so I hope we can agree on that. So now we have one side of the relation, but we still need to do the other side, what would you call it, the upper bound, in order to qualify b is equal to an. So let's assume x exists in b without all of the elements of an. Well, that would imply x is not in any ai for all I. And yet, x somehow ended up in b, which can't be possible because that would imply, well, a discontinuity. So, the limit of the sequence, this can't be in b if it's not in any a, given that, there are infinite sets a. So, that means x can't exist, because if it did exist, b wouldn't be equal to the limit of an, which it clearly is. So that means that, well, b without this is completely empty, which implies that b is a subset of this. And these two in tandem tell us b is equal to this union. And so we can just say this is MB, and we proved it correct. Alright, so now let's do the inverse. Let's say A1 is a superset of A2, which is a superset of A3, which is a superset of A4, and so on and so forth. A1 always contains AI. AI always contains AI plus 1. Okay, so now we're just going to show that intersection of all AI, the measure of the intersection of all AI, should be equal to the limit as n approaches infinity of the measure an, right? Well, there's a contradiction here. Well, no, not really. There's a counterexample here. Let's take a1 is equal to 1 to infinity. Can't do that. A2 is 2 to infinity. A3 is 3 to infinity, and so on and so forth. An being n to infinity. And so clearly an plus 1 contains an. No room for equality. But this doesn't follow this rule. How? Well, let's see. The measure of this is infinity. The measure of this is infinity. The measure of this is infinity. In fact, the measure of all of these sets is infinity. Hence, the measure of the limit should be infinity. And yet, the intersection of all of these sets is 0. Why? Well, let's say x is in the intersection between all of these sets. But that can't be true, because then I know that x is not in ax plus 1, which only runs from x plus 1 to infinity. So yeah, it doesn't exist. Which means that somehow this is 0, since this is the empty set and the measure of the empty set is 0, yet this is infinity. That can't stand. And that's because the continuity of the Lebesgue measure function breaks down at infinity. If we state that MAN cannot be equal to infinity, suddenly this problem becomes tractable in the exact same way that the previous problem was. So that's a very interesting exercise to show why Lebesgue measure is a little bit enigmatic and its interesting properties because it's a generalization of length, very informal concept.